to get back to that, we double it 6 times. Right, to fill this in. Thank you. So this is going to go 2, 4, 8, 16, 32, and 64. So it started at the initial activity was 64 microcuries. Okay, cut in half 6 times to get to 1. Yep.
I actually have a question about the one above that.
Sure.
Do you not have to take into account the 3?
Oh, no, you do. Thank you. You're right. That's not right. Because I didn't see that. Thank you. So you got to take into account that there's 3 more there. So instead of 146, it should be 143. Because all the numbers on both sides have to add up. So 143 plus 90 plus 3 is 236, which is 235 plus 1. That's what you see on the other side. Okay. And then converting that to microbecquerels, this is just a regular conversion question. So 64 microcuries. Oops. Curies is CI, not C. Oh, I got that wrong in the question too. Sorry. We need a fraction that gets us from microcuries to microbecquerels, and that is the conversion that's given. So 64 times 3.7 times 10 to the 10th might be a difficult calculation for certain calculators. So you can do it like this. You can go 64 times 3.7, and then just add on that times 10 to the 10th. So that's 237 times 10 to the 10th microbecquerel. And that's not the standard way to do scientific notation. So that would also then be 2.37 times 10 to the 12th, because you got to move that decimal 2 more times to get from 10 to the 10th to 10 to the 12th. All right, so that was a quiz. Hopefully it went well. I will get those graded and posted as soon as I can. I know we're behind a couple of quizzes on Blackboard. All right, let's continue. When we last left on Tuesday, we were talking about organic molecules, talking about methane, these carbon-based structures that have this kind of different geometry from how we sometimes draw it. And then the last thing we did was we started thinking about these isomers, these different ways that we can arrange the same types of atoms to make different molecules. So today, we're going to talk about how we differentiate those in terms of names. We need these different structures to have unique names because, as this shows, saying C6H14 isn't good enough. That doesn't narrow it down the way that saying like NaCl narrows it down to exactly one kind of compound. The formula isn't enough to tell us just one kind of compound, so we have to have some more information there. So let's do that. All right, I'm going to kind of tell you the rules about naming compounds, how to do it, and then we're going to work through an example that way. We'll do that a couple of different times with a couple of different examples, and then you're going to try some on your own. All right, here's our rules. So number one, when When we want to know what a structure's name is, it's based on the longest continuous carbon chain in the molecule. So our first step is going to be to find the longest continuous carbon chain. And then name it. So let's do an example. Here's one of the pentane isomers that we looked at above. How many carbons, because the longest continuous carbon chain, so how many carbons are in the longest continuous chain in this molecule? How many can you count before you have to pick up your hand and go somewhere else? 4? See 4? And there's a couple different ways we can count those 4. We can count them like 1, 2, 3, 4. We can count them 1, 2, 3, 4. We could also go backwards. 1, 2, 3, 4. 1, 2, 3, 4. Right? So there's 4 different possibilities. For this step number 1, any of those will work. Doesn't matter. So let's just pick the non-obvious one, which is here. We could have picked the one straight across, doesn't matter. But sometimes we get tricked by these little turns that the thing can take. So let's pick that one just to remind ourselves that it's okay to take turns as long as it stays continuous. Okay, that is a chain of 4 carbons. Does anybody remember from Tuesday what a molecule with 4 carbons is called? That's the shape of it, but like which molecule is it? Remember all those different names? Methane, ethane, all this stuff? What's the one with 4? Go back up to our list here. So 4 carbons is butane. Yeah, thank you. All right. So that means that the main base part of our name is going to be butane. And we put that at the end. That's the end of the name. That comes from the fact that there are 4 carbons in the longest chain. The book has a nice table of all of what they're all named from 1 up to like 10. The objectives on Blackboard say you need to know up to 6. So that's methane, ethane, propane, butane, and then pentane and hexane. So after 4, all the names use those standard prefixes like pent and hex and hept and oct and that kind of stuff. The first 4 are the weird ones. Okay, so we got butane. But we can't just call this molecule butane because that's a different molecule. And we haven't accounted for one of those carbons. So we're going to do 2 more things to try to complete this name. The second step is we're going to number the carbons in the main chain that's the chain that we found from part 1. So that, and I'm going to use a different word here, the substituents, we'll talk about that in a second, are attached to the lowest possible number. Okay, so what does that mean? First of all, what do you think a substituent is? Maybe make a guess of what we're talking about there based on what we have and haven't named. It's just the things that are hanging on that chain. So the different pieces that are attached to the main chain are called the substituents. they're going to be different things depending on the molecule, but just those things attached to that main chain are called substituents. So in this case, that CH3 is the substituent. See that one over on the left there? It's not a part of the main chain. It's coming off the main chain. So how do we want to number this chain? Do we want to start at the bottom CH3 and number up and then to the right? Or do we want to start at the right and then number to the left and down based on this rule? Yeah, based on this rule, we want to start down here and go 1, 2, 3, 4. Because that puts that extra CH3 substituent on number 2. If we went the other way, that would be on number 3. So this way gives us the lowest possible number. So you're always going to number sequentially along the chain. You can't like jump around from carbon to carbon. But you can start from either side. So you have to pick whichever side gives you the lowest numbers for the substituents. And then finally, let's see how that's worded. We're going to identify and name those substituents with the number they attach to. So how does that work? Okay, so we identify the substituents. We say, I see a substituent. Here's a thing that is hanging on that chain. That is a substituent. And then we have to name it. So what type of a substituent is that? The types of substituents that we're going to mostly see are a CH3 hanging off something, a CH3CH2 hanging off something, or maybe in some cases a CH3CH2CH2 hanging off of something. And those names are based on the same names that we used earlier, but because they're a substituent, the name gets changed a little bit. So instead of calling CH3 methane, we call it methyl, M-E-T-H-Y-L. Instead of calling a 2-carbon substituent ethane, it's ethyl. And then a 3-carbon is propyl. And those all have to be connected in order like that to get those different names. So as we'll see in some examples, if there's some different CH3s around the molecule, those are all individual methyl substituents. If they're connected together as one substituent, CH2, CH3, that would be an ethyl. And we'll see some examples of both of those. Okay, so in this particular compound, we see that there is a methyl substituent. And which number carbon is it attached to? So the rest of the name becomes 2 from this carbon number 2, and then a hyphen, 2-methylbutane. So that works? All those pieces are important to the name. That makes it unique. That tells us we are only talking about this one particular compound, and that is what it's called. All right, let's look at another one. This is another one of our pentane isomers. Okay. Let's follow that same procedure. So the longest chain here is how many carbons? 3? Everybody agree? Does it matter where we count our 3? It doesn't. They're all 3. So what's your favorite? Straight down, top to bottom? Okay. All right. There's our 3-carbon chain. And what would we name that?
Propane.
Propane, yeah. Oh, I think I angered it. There we go. Propane. Great. All right, let's number the chain. Should we number it from top to bottom or from bottom to top? Based on where those substituents are. Those extra things hanging on. Doesn't matter. So what do you like?
Bottom up.
Bottom up? Be contrary to standard way. Okay. So bottomed up, we got 1, 2, 3. Now we identify the substituents. I see substituents here and here. And by the way, none of this like marking stuff is actually like required to make a name, but I think it helps to find the name. So if you just look at a structure and know what name it is, that's fine. All right, so I find 2 different substituents. The fact that I see 2 substituents tells me I'm going to need 2 different numbers in my name. It also tells me, well, let's also look at then what type of substituents they are. So what type of substituents are those 2? They are methyl, and they're both methyl. So even though there's 2 of them, they are separate substituents. They are separate methyl substituents. There's a common mistake to see that there's 2 carbon substituents. So let's just call that ethyl, because ethyl is 2 carbons. That's wrong. They have to be attached together to be ethyl. Since they're not, there are 2 different methyls. And the way that you name something like this with 2 different methyls, each one gets its own number. So you go 2, 2 to indicate that there is one substituent on carbon 2 and another substituent on carbon 2. And then we say dimethyl to indicate that there are 2 methyl substituents. All right, let's look at another one. Okay, give this one a try on your own first. See if you can follow through those steps. Find the chain, number the chain, find the substituents, and then put all those names together. And let's see what we come up with. All right, you got something? Okay, you don't have to tell me what you got. I'm going to go through it the way I would do it, and then let's see where we match or don't match, and talk about it. So I got to find my longest chain. can pick any group of 4 carbons in this structure. Anybody find a longer chain than 4? I'm going to go with this one. Okay, if you went straight up, down, that's fine too, or like kind of zigzag, whatever. Any group of 4 carbons should be fine. All right, so then I'm going to number it. In this structure, it doesn't matter which end I start with. I end up with the same substituents and the same numbers. So I'll just start here and go 1, 2, 3, 4. That puts my substituents on 2 and 3. They are here and here. Okay, let's construct a name. So 4-carbon chain is butane. I have 2 methyl substituents, so that is dimethyl. And then those substituents are on carbons 2 and 3. So that gives me the full name. Is that what you got? Great. Okay. Let's talk about a couple more types of substituents that we might see, and then we'll move on to some bigger structures and see what you can come up with. Other substituents, common ones, are the halogens. That's the group 7A elements. So let's list those and what their names are as substituents. We've got fluoro, chloro, bromo, and iodo. And we'll see those on some structures as well. All right, before we go on and look at some more of things with that in it, let's go back up to our isomers. We've done the first row here, and we've done one of these, this one right here. See if you can name the remaining 4 isomers of hexane. Those isomers we drew last time. Yeah.
I'm sorry, what was the iodine one called?
Iodo. Iodio. Got some names yet? Yeah? All right, let's see what we got. So the first one, I'm going to type this just because I don't have enough room to write under here. This is just going to be called hexane. It's a straight chain of 6 carbons, hexane. It might sometimes also be called N-hexane, a little N in front of it, which sort of means like normal hexane, just plain old hexane. Okay. Hexane without anything else on it. So this one then becomes 2-methylpentane. Three-methylpentane. Two-dimethyl butane. And 2,3-dimethylbutane is the one we already did before. Okay, so if you got some of those wrong, if you don't mind, where did you go wrong? Yeah.
For the 2,2-dimethylbutane, I put 3 because would that matter?
Yeah. So so this was your main chain, like going straight across like this. And then we have to decide, are we going to number from the left to the right or from the right to the left? So if you number from left to right, you get 3, 3. If you number from right to left, you get 2, 2. The rules say we always want to go with the lowest number. So that means starting from the right and going to the left, in this case, is a better way to go because now we have lower numbers for our substituents. Any other things that you saw that didn't work?
Pentane and hexane.
Okay, so forget what pentane and hexane were. Yep. So we have to look those up. All right. Let's try some other. Sure. Yep. Try a couple more examples and then before we move on. All right, what do you think about this one? So I want to draw this one a little bit differently. Sometimes what you'll see is it kind of condenses the whole structure, but just still leaves some lines where something kind of branches off. And we don't want to get distracted by that. Anything that's bunched up against something else right next to it is still continuous with that chain. So we can think of those carbons as being bound together. So see if you can come up with a name for this one.
Would it be counted as like 1, 2, 3, or would it be 1, 2, 3, 4, 5?
What's longer?
I mean, like when there's not a line but like
Mhm.
they're connected, do you still
You can
have to
still
count
consider that those
separate?
are connected. No, you would still count that as part of it. So your main chain should be either 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Those are all connected. So those would all be, yeah.
Okay.
The only thing that can't be a part of the chain is the bromine. The other way you can count it is like this: 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Yeah.
Isn't that in substituent right first?
I don't care that much, like for this class, but the convention is to do it in alphabetical order. All right, got some names? Do you want to tell me your names, or you want me to tell you my name? Okay, I'll take that silence as I'll tell you my name. Okay, let's see. I'm going to pick a longest chain, which is 5, and we can pick from any of those 5s we talked about, but here's one. That tells me that this is a pentane. My substituents then are this one and this one. That is an ethyl and a bromo are the two substituents. Now, where are they? We need to number the carbons to find out. Where should we start our numbering? Doesn't matter, right? Because they're both on the, also I didn't do this right. There should be a 2. They're both on the same carbon right in the middle of the chain. So we go 1, 2, 3, 4, 5, or we could have started from 5 and gone 1, 2, 3, 4, 5 the other way. Same thing. So that means we have ethyl and bromo on the substituents. The way we write that is we write 3 bromo and then 3 ethyl.
If one of them was on, let's say the two,
Mhm.
if it was a different thing, would it be like, would you say 2 bromo, 3 ethyl, or would it still be,
It would still be alphabetical order.
okay, so even if the numbers.
Even if the
are-
numbers would be, you don't have to put the lower numbers first. It's alphabetical order. That ordering thing, I'm not going to worry about that too much in this class. I'm not going to worry about it at all in terms of quizzes and exams, because I feel like if you have the numbers and the substituents, you have a unique name for the structure. It can only be one thing. So what order you write it in doesn't end up really mattering in that case. The neat thing about this is because it's systematic, because it's a set of rules, any molecule that you can come up with, anything that you can draw, that you can look at, that you can make in the lab, you can come up with a name for. You don't have to just know some weird old name that's taken root for some reason. One thing that we use sometimes when we have really crazy structures, we used that 3D software the other day on Tuesday to model that shape. Whoops, let's say we can do it again, but we can't do that here, so we got to do that in a different thing. There's another piece of that called ChemDraw, which we use for drawing structures and for publication and that kind of stuff. But I can draw some crazy things like these are all carbons, and we're gonna learn about these structures soon enough. Like connect them in weird ways. Somebody doesn't like that one. Okay. Cool. Draw some kind of crazy thing where these are all carbons with hydrogens coming off of them. And I can ask the program to name this structure. And because the rules are set up in there, it can come up with a name. It's kind of a crazy name. I mean, it's just a long name. It's not nothing wrong with it. It kind of looks like the stuff that we've been naming, right? With some different words because of how long it is. But it's the same idea. You follow these rules and you can name anything. And I think even we can update the structure and have it change the name. So like if I break some of these rings open, it now changes the name to something that is pretty similar to what we've done. There must still be something weird somewhere. This big word hexacosane is just because there's so many things in the chain. But following those rules, you can always do that. Okay. Let's talk about another class of alkanes that we can use in doing this. And that'll be where we wrap up today. The cycloalkanes. Cycloalkanes are what we get when we connect the ends of a chain together. So here is hexane, or let's do pentane. Here's pentane. With 5 carbons. We know that one. And then here is cyclopentane.
You have less hydrogen.
Yes, we have less hydrogen
Because
in a cyclic alkane or a cycloalkane because the ends have to connect. We have to keep 4 bonds on carbon. So you'd have to pull those 2 off the CH3s so that they can connect back together.
where do they go?
They're different structures, so they didn't. It's not like one turned into the other one. I just wanted to show that the names were similar. Yeah, they're not isomers because they have different molecular formulas. So pentane is C5H12, H12, And cyclopentane is C5H10. Because you have to have a couple fewer hydrogen to get that ring closed. So what do you think is the smallest cycloalkane that you can have? What would it be called? Could there be a cycloethane? If you had 2 carbons, can you make
Oh,
a ring?
think,
You can't really, right? So it's got to be what?
propane.
Yeah, cyclopropane is the smallest one. And an interesting thing about cycloalkanes is how they can kind of change their shape as they get bigger or change their angles. Remember we talked about the bond angles in carbon? What did we say was the ideal angle there from the tetrahedron? Can we remember? One about 110. What's the angle in a triangle? Anybody remember their geometry from years ago? At some point in your life, you probably knew the angle from inside of a triangle, of an equilateral triangle. Anybody remember?
Like 60?
Yeah, 60. Remembering. Yeah, so that's 60 degrees. That's way less than 110, which means that in order to make a cyclopropane, you have to really kind of squeeze those things to be a lot closer than they want to be. And that makes cyclopropane kind of a reactive compound because that really wants to open up and relieve that stress. That's called bond strain or angle strain. And you're straining these bonds to try to make the structure. If you go to cyclobutane, now what's the bond angles? 90, yeah. So now we're a little bit closer to that 110, a little bit more stable, still not where it wants to be. Cyclopentane gets closer. And actually, the most stable type of cycloalkane, the most common one, the one that's in our body that makes a lot of our compounds like carbohydrates and hormones are based on these types of structures as well, is cyclohexane. Oh no. Let's see if we can get it to respond here. Well, anyway, while that's going, cyclohexane has 6 carbons. Probably out of memory or something. But if you had 6 carbons, you make a hexagon. Can't draw it right now because the program's broken, but you make a hexagon. What's the angle inside a hexagon? Yeah, 120, because you can think of it as made up of adjoining triangles. So there's 120 in a hexagon, so that's actually bigger. So that means that bond should be stretched out. So why is that one much more stable? It's because it actually doesn't stay flat. So these cycloalkanes don't need to be flat, even though we draw them that way on paper. Cyclohexane actually looks like this. So if we're looking at it kind of head on, it looks pretty flat like a hexagon. But what it's really doing is something like this. You see how those carbon atoms in the middle go like up, down, up, down, up, down, all around the ring? That allows it to relieve that stress. And if we zoom in and look at just like one atom here, you can see that it actually looks just like that methane. It has that same tetrahedral geometry. And because it can relax and kind of bend like that, this ends up being exceptionally stable because it has that ideal bond angle. It doesn't have to stretch at all. If it were flat, it would have to stretch a little bit, but because it can kind of move itself around like this, it doesn't have to stretch, and it has those same types of bond angles. So that one's especially stable. Questions about this stuff so far? All right, so when we're naming things, we're still, all right, we're gonna have to close it. We'll get into this next week, but when we name stuff with cycloalkanes, then that cycloalkane becomes that main parent. So instead of 2,3-dimethyl whatever, it's 1,2-dimethyl cyclohexane instead of just hexane. And we'll practice that on Tuesday. So keep working through the homework in chapter 11. Yeah.
So the only way we use cycloalkanes system is if there are.
If they're connected in a, so like the ends are connected together instead of just